Hello! Hello, everyone. Welcome to the LIUniverse. I'm Dr. Charles Liu, your host. At this point in life, I would much prefer that you call me Chuck. It is always such a pleasure to be here today. We have a special guest I've been waiting for a long time to have a chance to speak with. But right now, let us first introduce, as usual, our co host, Allen Liu. Hey, Allen.
Hello.
Hey. Experienced any interesting wave backgrounds lately?
Uh, well, in terms of waves, I mean, you got the more literal water waves in Lake Ontario, where we went
That's right.
and
And
saw the
enjoyed.
eclipse, as you might have seen on our social channels.
That was fun. I was so happy to be there with you, Alan, and our family members and everything. We just had a great time. I'm so glad
It's great.
that we had a good time and did that. Yes, and as promised, our awesome guest today, coming from NASA Goddard Space Flight Center and the University of Maryland, Dr. Ron Gamble. Ron, Dr. Gamble, hello.
Hi. We're finally here, Dr.
I
Liu. We're
know.
finally here.
It's been forever. We've been talking about this for a long time, and it's so good to have you. And at the moment, are you parked in College Park?
I'm home, so I'm in my home office where
Uh-huh.
I would say where all the magic happens, but there's a bunch of equations behind me. But yeah, I'm in my home office.
For those of you who are on the audio only, indeed, behind Ron is a wall of beautiful equations. It is art in itself, and then there's additional art back there, which I would love for you to give me a tour of at some point later on in this episode. But let's just say that it's clear to me that even from the beauty of the equations alone, it's clear that you have a sense of what is beautiful and what is artistic, as well as what is scientifically beautiful. That's just my take. That's all I can say.
Yeah. Art math is certainly an art form.
I'd
At
agree with
this
that.
level, it's
Yeah.
definitely an art form.
Hmm. Completely. Okay, so let's get right to today's joyfully cool cosmic thing.
Yeah.
Uh, this is a little bit of a throwback in a sense that this original discovery was announced a little while ago, but I cannot wait to hear your explanation, Ron, because we need to understand it in a way that I think none of us have really had a chance to digest over time. And you are our expert, being the cosmological gravitational wave black hole meister dude that you are. So this joyfully cosmic cool thing of the day is the gravitational wave background.
Yeah.
Basically, for the past 7 or 8 years now, we've been making these discoveries that have produced remarkable results of things like black holes crashing into neutron stars, black holes crashing into other black holes, and they're creating these waves throughout the entire universe. But what is this background thing? It suggests that gravitational waves are literally everywhere and we just don't experience them and don't understand them. And that blows my mind. Please tell us what this actually was.
Yeah. So I'll preface this with Nanograph, and I met some of the people at Nanograph last year. I gave a
Yeah.
talk at University of West Virginia. It's awesome. I was
Mhm.
amazed. I was fanboying. Um, but
So Nanograph
Nanograph
is the
has,
scientific organization that made this discovery?
yeah, Nanograph's the project that made the discovery. And what they do is they look at and they observe what's called pulsar timing arrays,
Okay.
Mm.
PTAs. And those things, you can think of them as very bright objects. They're compact. Some have neutron stars or black holes, but they have these jets that come off and they're very persistent, but they flash like buoys or lighthouses. So they're
Ah,
like
Okay.
cosmological lighthouses. So now, if the universe is a sea of all of these different pulsars that are out there, they're like buoys in the ocean. And when a wave goes past, the pulsar will wobble. And then
Okay.
when
oh,
you look at
wow.
a whole network of pulsars, they'll all wobble periodically in a pattern. That's a pulsar timing array. That's how you can
Amazing.
detect some of these larger wavelength, higher frequency gravitational waves. That's the gravitational wave background that Nanograv detected. And
Wow.
I was out of my chair doing backflips watching that webinar. It's amazing what science we can do today. So
Wow.
that's
That's
what they
awesome.
found.
So these are like
Yeah.
natural timers, basically, because they spin so fast and because they're so regular.
Yeah, and now you can imagine if you have the buoy, you can attach a clock to it also, right? So we're talking
Oh,
about
wow.
ripples not in space, we're talking about space-time.
Okay.
So these are ripples
Yeah.
in space-time coming way across the galaxy, across the universe. But
Wow.
they give us kind of like a carbon date for the universe as well,
Okay.
if you will. So now we can look at the relic of the background. Much like the CMB, the cosmic microwave background,
Mhm.
we now have kind of a cosmic gravitational wave background.
Whoa. Does it give the age of the universe too, just like the cosmic microwave background does?
It gives us clues about the age of the universe and where these waves were generated. How are they kind of, stochastically kind of ringing together? When you think of gravitational waves, we can't think of the same thing as light, right? You can see
Right.
light, there's a light bulb, I have a ring light in front of me. But
Mhm,
gravitational
mhm.
waves, you have to think of them as sound.
Oh,
So for the sound, what is the universe singing? What song is the universe singing?
Nice.
Basically, that's what Nanograph picked up.
wow.
The
Now, does
background choir, if you will.
I'll tell you, I
Wow.
have on the very first gravitational wave detection from LIGO, or one of the early ones, they made it into a little chirp sound. I actually made that the notification sound on my phone.
Ah,
Because it's,
so that's what I hear all the time.
yeah, the
Is
little
it a
whoop.
whoop?
Yeah.
Oh, man.
Yep.
Good job. I'm a big fan of that kind of thing. Wow. So if it's sound, Ron, does that mean that it has anything to do with the so-called baryon acoustic peak? The baryon oscillations?
Not quite. We say sound because it's the analogy here is that a gravitational wave would mechanically displace objects,
Mhm.
right?
Mhm,
It'll
mhm.
stretch and shrink, kind of like this, right?
Okay.
Much different than light, right? Sound is a mechanical wave. Gravitational waves are more or less mechanical, right? But what's different between gravitational waves and sound, gravitational waves don't need air to kind of
Ah,
vibrate through,
Mhm.
right? Much
ah.
like sound. There's no
Mhm,
sound in
mhm.
space, right? We can't hear anything per se,
Yeah.
but we can feel a gravitational wave go by. And we can take
Wow.
that data and transcribe it into a sound, just much like the chirp mass that you
Yeah.
hear. Yeah.
Wow. That's amazing. Surely it's not a very huge effect because otherwise we'd already feel it by now, kind of like the earthquake that struck not that
Yeah.
long ago in New Jersey. Hmm.
Yeah, so it's a very subtle effect, right? So
Mhm.
if you think of like a light rumble in the background.
Yeah.
So if you can ever think of the analogy here as like the rumbling before a storm starts.
Okay.
That's like the gravitational wave background of the universe. That's the rumbling of the universe. What's going on here? These are
Cool.
the things that go bump in the night that we're
Nice.
trying to figure out.
And when you're
Fantastic.
talking about the high and low frequency of the gravitational waves being found by people like Nanograv group there, that is that the analogy then to the high and low pitches of sound, because they're running at these different frequencies and these different
Very
wavelengths.
close, but once we start getting into kind of that analogy has a little bit of limitation because different combinations of different ratios of masses and geometries and things like that, they will radiate different types of gravitational waves.
Okay.
So some
Ah.
waves that are generated by the background are
Hmm.
almost mirroring things that are like extreme mass ratio in spirals, right? Where a very
Nice.
massive black hole pulls in a star or something else,
Okay.
Uh-huh.
right? So those things, they're not the same gravitational wave, but in terms of detecting them, in terms of our technology, it's very hard to decipher what is what. So
'Cause we're so new at this.
that's
Mhm.
why we're so new at this, right? That's why it took so long to actually test
Yeah.
this.
Yeah.
But we've got Nanograph looking at things, and they're doing an awesome job. Lisa just got
Yeah.
adopted,
I got a
so
laser pointer from them once.
Yes.
exactly. So
You got
that's
to
gonna
tell us about that. Yeah, we're going to hear more about Lisa right after I ask Alan if there is a question from the audience for Dr. Gamble.
Yeah, so we've got a couple questions here. The first one I'm going to ask comes from Kelly, who is asking, do gravitons exist?
Oh.
okay. So I have to. Okay, here's my watch, and I'm
Uh-huh.
setting a timer for 30 seconds because that's all I can do. Gravitons. I have to say gravitons. Gravitons do exist. That's the
Okay.
easy one.
Do.
They
Ooh.
should exist. I should say that.
All right.
Okay. Well, wait. What is a graviton? I mean, I have a sense of like a subatomic particle that carries gravity, but is there anything more to it than just that's what a graviton is?
Yeah, there are four fundamental forces of nature, right?
Hmm.
Electromagnetism, the strong and weak nuclear force, and then the fourth one is gravity.
Right.
We have detected those three particles that kind of mediate those other forces.
Mhm.
We've not detected gravitons that mediate the force of gravity on a quantum scale.
Uh-huh.
Right.
So I say they should exist because we have general relativity. It works very well. We are not falling out of our chairs or floating off.
Yeah.
So gravitons must be condensing and keeping us here somehow.
Okay.
Some way they're mediating the force of gravity. Now, are they going to present themselves as we think they will be? Maybe not.
Okay.
Because we've not found them yet, and we've been looking for a very long time.
Yeah, fair.
But that, in essence, a graviton is a classification of particle called a boson. So it would have, much like the photon is a boson, it's got spin 1. A graviton will have spin 2.
Okay.
That's what we call a
Oh my
tensor
gosh.
boson.
Oh, that's
Yeah.
dramatic.
So it is beyond the standard model of physics.
So at the
And
moment, there are no other proposed tensor bosons?
not ones that kind of fit as well as a graviton would, right?
Okay.
So a
I
graviton, we know a good bit that we should expect where we might find one and what properties it should have.
Yeah.
But if we find a particle that has those properties, then I can bet, my house that that's a graviton. But
That's fair. Yeah. So
Yeah.
as a math person, when I hear tensors, that makes me think of a matrix, right? So you have a two-dimensional or more than two-dimensional array of numbers versus a vector, which is the one-dimensional array of numbers, versus a scalar, which is a single number. How does that work for like a particle? What does that mean for a particle to be a tensor as opposed to a vector or a scalar particle?
Yeah. So it means and the very simple example I'll give you, and I'm trying not to go off on a tangent.
Yeah, that's
But the Higgs boson
yeah.
is what we call a scalar particle, right?
Okay.
It's a boson, but it's got spin 0.
Okay.
Okay, so just one number. A fermion, right, or the W and Z bosons for the weak nuclear force,
Yeah.
it can acquire two different states for spin,
Okay.
right? Plus or minus. So there's two particles, many different states to spin, but they're all kind of symmetric, kind of linear, right?
Okay.
So we call that a vector boson because it can
vary
occupy
sort of along
those.
this one dimension.
Yeah. A tensor boson says that I can occupy many different states.
Okay.
So a tensor boson would kind of have many different configurations that would give you the field of gravity on a quantum scale. So that's the difference. And I've gone over a whole bunch of math here.
Yeah.
That we'd be here for another 5 days explaining.
I would love to do that sometime, but I don't
that
want to monopolize your
that's
time.
Right.
Yeah,
That's in essence the difference. On a very fundamental level, that's the difference.
Wow.
That's awesome.
That is so cool. I am so glad that we're able to put these extremely weird, difficult, and fun questions to you. Your background to have gotten to this point and have so much knowledge about these really complex, abstract, and distant things. It must be amazing. Tell us, like, how'd you get to where you are today? Like, what path did you go to get to being this NASA cosmologist?
Yeah. So this started probably when I was 4. I asked my mom, "Does the sun have fire?"
Nice.
Yeah, and that's a nice, funny story where I start.
Uh-huh.
Fast forward into college, right? Because high school
Yeah.
was a blur. Fast forward into college, I looked up, what are the unsolved problems in physics and astronomy?
Okay.
And one of those things was, we don't know what quantum gravity is. We don't exactly know what dark matter is, dark energy, what's inside of a black hole. Is there another form of gravity that a black hole can do? So I had all these different questions that no one had answers to. And I asked my advisors, and they said, go read a book. So I picked up, I don't have it in front of me, but I picked up Meisner, Thorne, and Wheeler.
Gravitation.
Yeah. The Gravity Bible.
Nice.
And I just started reading. And by the time I got to my junior year in undergrad, I decided, I want to study gravitational waves and I want to do black holes and general relativity. But I had no idea what math I needed to do to study all of that, So I started very early reading things I didn't understand, and I would just take notes. And eventually, I'm like, okay, well, I'm going to get this definition, and differential geometry would become a little bit easier and easier
Nice.
until it started making sense, and then
Wow.
everything started to click.
That's
So I
awesome.
actually started learning the math I would need in grad school 2 years before I got to grad school,
Wow.
because I knew I needed those 2 years to get a jump start to do what I really wanted to do. So I
That's a
studied
great point.
nonlinear gravitational wave theory in grad school.
That is amazing.
Marvelous.
Yeah.
And you knew, I mean, this is actually a big deal. The way you described it, you knew that you needed more time. It wasn't like suddenly you could just show up in a class and understand it all immediately. And I think a lot of students are afraid of that, right? Like if they're not good at something the moment they walk into a classroom, then they must be bad at it, and therefore they won't try it, or they're afraid of it, or something like that. But what you're saying is you saw it coming, and you said, I'm going to allow myself to have the time to build those skills and to exercise those abilities until you were good enough to get it done. That's great.
Yeah, and I will say it wasn't all rainbows and gumdrops.
Yeah, fair.
Right? Freshman year, undergrad was a big kind of eye-opening moment. I had to take calculus 1 3 times. I took calculus 1 3 times. And a lot of people don't believe me when I say that. I was like, yes, do not let all of this fool you. I had to relearn. In undergrad, I had to relearn how to learn math and science.
Wow.
High school, middle school, it all came really easy.
Mhm.
But once I got to college, the hard things, I had to learn how to learn. And that was the pivotal moment. And then everything else just became like building Legos now. I'm like, okay, well, I remember this piece, and I know Riemannian geometry and metric spaces and all these other things, and the
That's
Ricci
fantastic.
curvature tensor and all that. Yeah.
Ricci curvature tensor. Oh,
yeah.
my general relativity is coming back to me in a flood of images and memories.
Right.
I just remember the Ricci tensor was a capital R, which is good, but there was a Christoffel symbol, which looked like a gallows. And I was like, am I meeting my doom doing the Christoffel symbols? It was amazing.
Yeah.
Oh my gosh. Wow. Good for you for getting through that. And that is a tremendous challenge. And, you mentioned Riemann geometry. That's known in the history of physics because Albert Einstein himself, to develop his first version of the general theory of relativity, needed to learn that stuff too, because he also didn't have it when he was first thinking about the problem, right? It's really amazing. And Riemann, Mr. Riemann, Professor Riemann, Dr. Riemann was his professor. But even then, he hadn't learned it yet, and he had to learn for a while longer before he got it done. Wow. But now you see through the whole universe, right? Your current research is piercing through that veil, right? Tell us about some of the things that you're doing on pen and paper or with a computer.
So right now I'm studying the theory and the physics behind relativistic jets. So these are things that are similar to pulsars, but they are whole galaxies now, right?
Mm-hmm.
Yeah. They're supermassive black holes, but they have these very long jets that come off of them. And the material is moving at near the speed of light. We're talking 99.9999999% the speed of light. So it's very high, very, very high velocities, very relativistic, ultra relativistic, if you will.
Okay.
And they're very bright. So these objects, if they're facing at us, they're called blazars. So that is what I'm looking at. But what we don't know is why the jet comes off of the black hole. So taking that kind of kiloparsec, megaparsec jet and shrinking it all the way down to just above the event horizon. That's my Goldilocks of physics that I'm trying to figure out.
Trillions of miles down to like 1 mile.
Essentially, yeah. So we call that the single parsec problem. So that is what I'm trying to figure out and contribute some new science to.
So getting a jet off of a black hole is the problem.
Mhm.
That's outstanding and unknown. I mean,
It's unknown. Yeah.
simply thinking, right? We know that once you enter past the event horizon of a black hole, you're not coming back out. But you're saying that just before you reach that, there's some mechanism that causes jets to shoot away from the black hole at this enormous speed.
Yeah, so you can think of them. I like to call them, and I think I've coined this. I haven't heard it anywhere else, but I
Okay.
like to call them black hole lasers.
Yes.
So if
Ah,
you think of a laser, it's the same kind of the same physics. So that's what I'm looking at.
Oh, awesome.
Um, and they are. We don't know why they come off, and we don't know why they're so focused. They're so culminated across very long distances. We have no idea why that happens. But we do have an idea that it's linked somehow to the rotation of a black hole.
aha.
So thank you, Roger Penrose and Reva
Yeah.
K. Williams and all the people working on those theories to figure out, okay, well, what's going on here, right? Where does frame dragging come into play? I'm like,
Oh, that's
Mm.
fun
okay, well, we
stuff.
have to figure that out, right?
Yeah.
More math.
Yeah. Well, Roger Penrose, of course, known for all kinds of cool, interesting questions in tiling, tessellation. He won a Nobel Prize too, did he not, for his first thought process?
Yeah, he did, and it was him and Dr. Reva K. Williams kind of proved his theory correct.
Yeah, tell us about
That
that.
confirmed
Yeah, tell us about Reva
the
K.
Nobel
Williams.
Prize. Yeah,
I
so
just don't know enough.
she was actually the first black woman to get a PhD in theoretical astrophysics in the U.S. A
Wow.
lot of people don't know. Yeah, so we have like a hidden legend just kind of just existing, and I'm like, okay,
Yes.
when am I going to meet her?
Wow.
But hers and Roger Penrose's work was centered around the
Uh-huh.
idea of extracting energy from a rotating black hole. That's
Yeah,
as
I've heard
simple as
about
I can
this.
explain it. Can we
Wow.
do that, and where does it go?
I
Well,
see.
if I have a particle pair, electron, positron, right, and they're both bouncing around the black hole, if one falls in, it's going to kick off the other one.
Okay.
Okay? Well, we're going back to this idea of angular momentum now. If I drop
Yes.
one in and one escapes out, but they were a pair, right?
Yeah.
Mhm,
Then
mhm.
I am removing spin from the black hole.
Okay.
That's
True.
energy.
True.
If I do this a trillion times, right,
Yeah.
over a shower of particles, eventually that rotational energy will be removed from the black hole significant enough to either slow it down or have it being jetted off somewhere.
Wow.
So that is
Yeah.
what we're trying to figure out. Yeah, and it's very exciting, and I'm getting like all
Oh,
giddy
no.
about it.
It's wonderful. So both of them were awarded the Nobel Prize. Is that correct?
Only one of them, Roger
Oh.
Penrose.
Well,
Oh, no.
Yeah,
what happens? Oh no.
sometimes it happens.
Uh-oh. I'm starting to get a little annoyed now.
Yeah, I know.
This is a okay, not to get too deeply into this, but we always wonder, like, when people are awarded prizes like that, right? It's not like you're passing a finish line and you clearly came out ahead, but there are people who decide who have given the contributions and significance and things like that. And there are many stories in the history of science where
Mhm.
people who did similar work or participated together in the work, somebody was awarded the Nobel Prize and other people were not awarded the Nobel Prize. Is this one of those kinds of situations? Is that a fair thing to say? I don't want to get too deeply into it, but I definitely want to make this do, because if there's someone who should be receiving a little bit of recognition for their work, I want that to be known.
Yeah, it is one of those situations. And again, there's if you're not involved in the story and how it happened, there's some details that we don't know about.
Mm-hmm.
That I would say. But in general, these things do happen. It's very unfortunate. But one thing I like to tell the students that I mentor is talk about your science. Put it out, write papers. And you're never too early to talk about your science or ideas and publish them. And we can all put something on the archive or something. That's why it's there. But also, take ownership of your work. If you see something going wrong, then speak up. But you have to have others to advocate for you as well. So we can't have this process continue. So
Yeah, thank you very much for that. All right, let's bring in another question.
Yeah. All right. So we got another question in the cosmology end of things here from Nicholas, who is asking, is the Big Bang in trouble?
Oh man.
Oh, yeah. This is no doubt because in the news with various discoveries by the James Webb Space Telescope and so forth, and other places, right? JWST and other suggest that maybe the Big Bang theory has holes in it that cannot be fixed. Is that true or untrue?
I would say it doesn't have holes,
Ah,
or it's not necessarily in trouble.
Okay.
It's just incomplete,
Okay.
right?
ah,
So
okay.
I would say that there's very, very good evidence. And again, I'm kind of highlighting another Nobel laureate here, John
Mhm.
Mather, who was on the Kobe
Yeah.
team, and
Ah,
this
yes.
was their work, right?
Uh-huh, uh-huh.
And so I think we have pretty good evidence that some cataclysmic event happened,
Okay.
right? General relativity, again, my wheelhouse. It
Yeah.
Mhm.
predicts some fairly substantial evidence that something, again, supporting that event happened.
Okay.
Whether it's a big crunch, right? Something that very crunched together and it expanded out, or something that's just immediately exploded, immediate expansion, right?
Yeah.
Hmm.
We don't know what it was. No one was there 13 billion years ago.
Yeah.
We can't dig anybody up and ask them. But what we can do, right, is figure out, well, what's happening right now around us. We know the relative expansion of space is happening. We know it's accelerating. We know dark matter exists, right? So we have a pretty good idea of cosmology.
Yeah.
It's a thing now, right? So
Right.
we have many different flavors of it also. But also we're doing experiments. So we can test this.
Right.
You
Yeah. We
know,
can look for those
it,
after effects.
yeah, and it's as easy as somebody writing a pretty creative proposal, right, to put this experiment together and test what happens. Of
Yeah.
course, no black holes, but let's see what happens. I'm kind of optimistic to where the theory is going to take us,
Mhm.
right? How creative can we be in the math and the physics?
Yeah.
Wonderful.
We can figure this out.
So the idea is we know
Oh.
something happened. Like
We
you
know
say,
something happened.
something
right?
happened, and it was probably big and involved some banging. But
Right.
but whether it's the Big Bang as one particular model of it, mathematically speaking, that might have been more accepted in the past. Maybe we need to tweak that model a little bit.
Yeah, and it could. Who knows what we'll find? We might find
Right.
the source of all lottery numbers, that one or something.
Yeah.
Oh my
Which
goodness.
would be crazy.
Oh, wow.
We don't know, right?
Yeah.
So more discovery out there. That's what I
Oh,
say.
wonderful. Oh, I think that's wonderful. Okay. It's time for us to talk about what's on that wall behind you there. Because, Ron, it's beautiful. It's marvelous stuff. And I'm not talking just the equations and the way that you've laid them out, but clearly you're an artist, and you've been an artist for a long time. Have you been an artist in the same sort of spirit and length of time that you've been a scientist?
No. So I actually started painting when I was 16.
Oh, okay.
Started I
So not
started
quite 4. So you had to wait
not
12 more
quite for,
years.
yes. But my mom she played the piano and she painted and she drew, so I
Oh,
kind of got it from her. And my
right.
dad, he drew. He was an illustrator of some kind on the side. So
Uh-huh.
we have a very artistic family.
Awesome.
Oh, wonderful.
So yeah, so
Eh,
let's kind of jump. I'm gonna
Yeah,
kind of
slide
rotate my
slide that
camera
camera. For
here.
those of you who are on audio, Ron is now just sort of rotating the camera a little bit and seeing different things. So be descriptive and sort of tell things. We'll start with that orange and um, I guess reddish shaded portrait that's right over your right shoulder.
Yeah, so that is
That is
something
cool.
that I did, and the date is November 2009.
Uh-huh.
So that was a little bit ago.
Yeah.
Um, but this was kind of like an era of my work, and it's in acrylic and oil. And a
Okay.
lot of times people don't like to mix those together because
Yeah.
it's a very hard pair of medium to mix together. But I
Okay.
figured
see.
out, kind of a very layered way to mix them together, and that's I was testing things out. And
Neat.
actually, a funny story is I ran out of oil paint, so I used acrylic, and I was like, okay, well, I'm a broke college student. I have to figure this out, right? We can figure this chemistry out. So this is the result of it.
That's cool.
Fantastic.
Excuse me. The others up here are kind of things that I like to attribute to my work being kind of like a visual journal,
Uh-huh.
Okay.
right? So at the time I was working, this one up here is titled "A Place We Call Home," and it's pretty much a commentary about kind of pollution and the environment in urban
Yeah.
settings,
For those of you who
right?
are just on audio in the audience, it's like a city street scene with brownstones and a road in the middle, but just a lot of greenish and whitish kind of vapor,
And
and things are a little
distortion.
bit
Yeah.
curly. Yeah, things are a little bit distorted, right? You've put that in there for a reason.
Yeah, and it kind of emulates something like an oil spill and how it would, it doesn't
Oh,
exactly mix and go away. It kind of deforms and displaces the water and things,
wow,
right? It's pretty,
wow.
sometimes it's permanent, especially, when it's affecting the life that's in the environment.
Right.
Yeah,
Yeah.
yeah.
This new one
Oh,
that's over
brand new.
there,
Aha! It, folks who are just listening to this, it kind of looks like, if I dare say, a mix between the DC supervillain Poison Ivy and the Marvel character Caliban. It's just a little bit cool.
it's
You
a
just got
little
to tell
bit,
me what it is.
it's unfinished. I'm currently working on it.
Wow.
But it will be a portrait of my girlfriend, Dr.
Oh.
Raven Baxter. So
Aha.
that's gonna be a very, very interesting piece of work.
Awesome.
And on the other
everyone,
side is going to be
everyone in the
something
yeah.
pretty cool. You can imagine a galaxy on the other side.
Oh,
That's what's
Wow.
going to
fantastic.
happen. So look out for that one.
And everyone remember the name Dr. Raven Baxter. Believe me, you will hear more of her on this show not too long from now.
So I actually, big surprise, and I've
Uh-huh.
been working on this.
Yes.
So this might be maybe the first place I'm revealing it, right?
Ooh.
Ooh,
Today is
excellent.
World Art Day,
Okay.
April
Okay.
15th.
Congratulations.
But today, I am launching my own online store. So
Wow.
I'm combining my science. I'm turning all of these equations into
Uh-huh.
artwork
I
Awesome.
that you
love it.
could buy. You can buy a t-shirt, a screen print, a hoodie, a bag, like
Wow.
kind of a tumbler like this. I'm making a whole bunch of things. So that is
Wow.
called the art of theory is what the store is called. And you can go to
Fantastic. And
theartoftheory.com.
the art of theory just sounds like a great idea.
Yeah.
It must be because you are deeply an artist as well as a scientist. And we've talked about this before, not on this episode, but elsewhere, that you've done like lots of stuff, including installation street arts with
Yeah.
Spider-Man battling Venom, and apparently they battled to a draw or something. Uh, but that must be like built into. I mean, the mixture of art and science. That's just so
It
cool. Tell us some more about
it is, and I've done everything from small paintings to kind of building sized murals. Um, but the art of theory stems from kind of people asking me, especially students asking me, well, how do you combine both the science and the art together, which
Yeah.
it. Yeah.
seem to be polar opposites, um, you know, do different sides of your brain? Well, it turns out that when you're doing kind of this work in theory,
Mhm.
your brain is actually using the same part. You're using the same part of your brain as you would to do art or paint.
That's
So
awesome.
Mm.
it's the same mechanisms, the same feeling, right, that you get in creating art. A brushstroke is the same thing as writing down an equation, a
Wow.
tensor, a matrix, a
That's really
vector,
awesome.
and solving that math, right?
You are living proof of what Albert Einstein said in 1930.
Yeah.
He published this thing called What I Believe. And in there, he said very clearly that the origin of all great art and science are from the same thing. You
Mm-hmm.
are that same thing. You are the embodiment of that same thing, Dr. Ronald Gamble. How about that, huh?
Yeah. So I came up with this idea, and I've been working on it for a while, and I actually tested a little bit out at Astronomy on Tap in
Okay.
New Orleans. Um,
Wow.
where I turned my presentation slides. I didn't want to do, normal black and white background slides. I turned them into a comic book.
Oh, that's really
Wow.
cool.
And so it looked absolutely amazing. It looked amazing. I was excited about it. It was on a large screen. But that was like, okay, well, I can actually turn this into something that people can have, right?
Mhm.
So people
Yeah.
can have a piece of my research on a t-shirt plus
Wow.
the artwork. They don't have to read through, all of our funky papers that go through peer review and we get headaches from writing them, but they can have the fun parts of our research, right? So
Awesome.
that's where the art of theory comes from.
Oh, that's great. And how does being a NASA scientist, like the pot of gold for so many of us, who want to do this kind of work, be a NASA scientist, how does that build into the whole art thing? I mean, is NASA happy with this, or
I mean, I would be
is
if I was
you?
NASA.
I would be too, but like, is your mission literally being added to because you're doing this extra thing, which many of us scientists don't do so much?
Yeah, so one thing that I am currently doing, I am the director of the NASA program, the Cosmic Pathfinders program,
Okay.
and that is kind of where I'm funneling all of my creative energy into. So much like how I would create a painting or create equations, I'm now creating this program in an artistic way to bring a whole bunch of students inside NASA with me, right?
That's awesome.
So all of the graphics, all of the advertisements, all of the posters that are created for the program, I create, and I've made it so that the artist communicating something very intentional to the audience, and that is
Wow.
those are things like science communication, where
Yeah.
you'd have a background of like the pillars of creation, but there's a typewriter in front. That's SciComm.
Yeah.
And things like imposter syndrome,
Mm.
Oh,
things like career navigation, where you have, you're standing in front of a railroad tracks. Well, where are you going with your career? Forward, I hope.
Yeah.
Yeah.
But things like that, attaching imagery to intention and impact. So
Wonderful.
that's what I'm doing. Yeah.
That's awesome.
Okay. Thank you. I mean, we have many other questions that we would love to ask you, but it will have to wait for another time because our time is wrapped up. But what a joy, what a fun time it's been with you. Thank you so much, Ron. Thank you, Dr. Gamble. I mean, it's been such a pleasure. How can we reach you? If we want to find out more of what you're doing, where are you on
Yeah.
social media? Where is your
We
websites?
had
Tell us where.
had fun doing this, Dr. Liu. So you can find me on all socials at Dr. _ Gamble 21.
Okay.
That's GAMBLE 21. That's
Awesome.
All right.
TikTok, Instagram, Twitter. And my website is www.theoreticallydrgamble.com.
Nice.
Very, very, very nice.
Yeah.
Wow. Alan, as always, thank you so much for everything that you do make this work.
Yeah.
All right.
Really glad to be on for this one.
Yeah. Ron, thank you again. Dr. Ron Gamble,
Thank you.
everybody. Woohoo! All right. And for all of you out there in the audience, thank you so much for joining us for this episode. If you like what you see and hear, please support us on Patreon. And as always, thank you for being a part of the LIUniverse.